Welcome to Formulaic Utopia. My name is Sarah, and today we are going to be exploring the question, what are the best strategies to use to win Monopoly? Yes, that's right, I said it. Today we are going to be exploring the old classic Monopoly board game, and we're going to be asking ourselves, what are the best strategies to use to win it? So let's jump in.
So, in order to understand the best strategies involved in winning the game Monopoly, you really have to understand probability theory. Now, why is that? So, the reason for that is really in understanding how you win Monopoly, you have to understand what is the long-term probability associated with landing on each given space on that board, because that determines a lot of the overall gameplay. So if we want to understand that, we first need to understand what is probability theory. So we're going to start off with just some basics. Okay, so given a sample space, we're going to call this sample space S. There are n possible events within this sample space, and we're going to just label these possible events, whatever they might be. We're going to label them E of 1 all the way up to E of n, representing once again in the total number of events within the sample space. Okay, so what would be an example here of a sample space? A potential sample space might be the sides of a die. So if you think about rolling a die, right, this sample space has 6 different events that can occur. You can roll a 1, 2, 3, 4, 5, or 6. All of those numbers represents the different possible events within that sample space. Okay, so now given this sample space, what if we wanted to find the actual probability of one of these events occurring? So for instance, if I wanted to find the probability of rolling a 1 on a die, how would I do that? Okay, so the probability of an event E, right, or the probability of rolling a 1, right, this is going to be probability of E, or probability of rolling a 1, is equal to the number of E outcomes divided by the total number of EI outcomes within the sample space. Okay, so to make sense of that, right, if we are calculating the probability of rolling a 1, that's going to be 1 divided by how many different possible events are in that sample space, which is 6. So we're going to have 1 divided by 6 as the probability of that event occurring. Okay, so now when we do this, there are always 2 conditions that have to be met. So the probability of an event occurring always has to be a number between 0 and 1. And the sum of the probabilities of all of the events within the sample space must equal 1. As long as those 2 conditions are met, you can find the probability of an event. So now that we have a bit of an understanding about probability theory and what that is, let's discuss a Markov process and how that also relates to finding the best strategies to winning the game Monopoly. And in particular, how it relates to finding the probabilities associated with landing on each space on the board. Okay, so a Markov process is a mathematical model which combines probability and matrices to analyze a process that evolves from one state to another, where the element of chance is always involved. Okay, and this process has 3 characteristic requirements. The first of which is it has to have countably many states. So the way that Monopoly has countably many states is you have a set number of spaces on the board that you can move to on any given turn. Number 2, starting at any state, you randomly change states where the state ended is only dependent upon where you started. And that makes sense in the game of Monopoly because you start at a given space. Let's just say maybe, for instance, Go. You're starting there and you roll 2 dice, which then tell you where you're going to move next. And there are also other things that can happen, like drawing community chess and chance cards that can take you to other places, rolling doubles, things like that. But at any given state, you still randomly change from one state to another. Okay, so that requirement is met. And number 3, each row within the transition matrix, which we'll discuss in just a moment, must sum to 1. So a Markov process always involves 2 different matrices, a transition matrix and a state matrix. The transition matrix represents the movement between different states, where the different states are various spaces on the game board. Okay, so for our transition matrix, it ended up being a 41 by 41 matrix. And the reason for that is because there are technically 40 different spaces that you can be on, that you can start your turn on in the game Monopoly. But the just visiting and in jail space, I went ahead and I broke that up into 2 separate spaces that you could technically be on. So I ended up building a 41 by 41 transition matrix. Okay, and basically the point of this matrix is that it's going to explain where a player can move to within a single turn, starting from any given space on the board. Okay, so in this 41 by 41 matrix, what we have is each row in this matrix tells us, given that, for instance, maybe I'm starting at go, where are all of the places that I can move to in that turn? Then the next row would be, where are all of the places that I can move to if I start my turn on Mediterranean Avenue? And the next one would be, where are all of the spaces that I could move to if I started on Community Chest, and so on and so forth, all the way through until you get to the final row of that transition matrix, which represents the final space, which is Boardwalk, and all of the places that you can move to, given that you start your turn at Boardwalk. Okay, and each row shows you a probability associated with going to any other given space, given that you're starting at a space. Okay, so for instance, if I'm starting at go, and I'm looking at the row for go, that's going to show me all of the different places that I can move to, all of the different spaces on the game board I can move to, given that I started at go. And what it's showing me at each given cell is it's showing me the probability of landing on that space given that I started at go. Okay, and every single row within the transition matrix is showing you this. Okay, so once we have this, we combine this with what's known as a state matrix. A state matrix is always a 1 by n matrix, where n, once again, represents the number of states. Okay, and a state matrix always begins with what's known as the initial state matrix. The initial state matrix, which we're going to denote as V0, and every other state matrix that follows is a probability vector where the elements of the vector always sum to 1. Okay, so the initial state matrix that you start with is going to tell you in a mathematical matrix where you start the game Monopoly. So V0 is equal to a vector containing 1 in the first spot, followed by 40 zeros. Okay, and this is telling us that we have a probability of 1, which means we are absolutely, without a doubt, at the go spot when we start the game. Then what we do is we take V0, that initial state matrix, and we multiply that by that transition matrix that we were just talking about. And what we get out of that is V1. Then we take V1, which is a probability vector showing us all of the potential places we could be at, given that we started at go. We take that V1 and we then multiply that times the transition matrix. And then from there, we get V2 out of that. And we just continue this process and we obtain a sequence out of this, which is called a Markov chain. And eventually, your Markov chain converges. Not in all processes, but in ours it did. We know that a Markov chain has converged when we have the following, where we have V of m, where V of m is just some number within this sequence, okay, is equal to V of m minus 1, so the prior iteration here, times the transition matrix. And then in the next one, we have Vm is equal to Vm times the transition matrix. So basically, once we find that a value is the same in the next iteration of the sequence, we know that we have reached what's called a steady state. And what a steady state tells us is the long-term probabilities associated with each given state within that process. So what's the probability really generally on any given turn and in any given gameplay? What's the probability that you're going to land on a certain face in the game? And so that's what the Markov process has given us using probability theory. So some assumptions that I ended up having to make is that community chess and chance cards are always reshuffled every time that a card is drawn, and that a player must immediately pay $50 to get out of jail before their next turn. And the reason for that is it just simplified the overall probabilities associated with each row within the transition matrix. Okay. So please know that those parts of the game are not technically involved in all of these assumptions. So now that we have covered our assumptions here, let's go ahead and jump into looking at the steady state probabilities associated with each space on the Monopoly game board. All right, so let's take a look at those steady state probabilities for landing on each space within the board. So in column A, we have the position number. That position number is just the number, the row number that it represents within the transition matrix. Column B is telling us the name of the actual space, and I have color-coded that according to the colors on the property sets. And then we have two different rows or columns here, excuse me, of probabilities. So the first column are the probabilities that I got out of my Markov process through multiplying that state and transition matrix until it reached that steady state. Column D here is probabilities that came from a simulation that was conducted by Dr. Ashley Meek. She did these, I believe, in Python, maybe MATLAB. And so this is just a comparison to show you kind of my own method and Markov process compared to a simulation, a coded simulation of it. And we can see that the probabilities that we get out of both of these processes are fairly similar to one another. And so that gives us a good deal of confidence that you know, what we have actually gotten out of this Markov chain is probably fairly accurate. So this is great. This is great news. So let's go ahead and look at this in a descending order. Like, let's look at this from an order of importance, right? Like, which one of these am I most likely to land on? Okay, so here we have a couple of things going on. I'm going to go ahead and hide some of these columns, and we'll talk about that in a few minutes. Okay, so these have been resorted to show the probabilities here in column C in descending order, so from largest to smallest, most likely to be landed upon within the game to least likely to be landed upon within the game. So I'm going to go through this slow for you. I'm going to scroll down, starting with in jail. In jail is the most likely to be landed upon at 4.5% of the time on any given turn, you're going to most likely end up in jail. The next most likely space for you to land, 3.19% of the time on any given turn, you're going to land on Illinois Avenue. The next most likely is going to be go, and that one is at 3.15%. And I know that these probabilities seem very, very small, but in all honesty, they're small because you're breaking a probability of 1 into 41 different spaces. So they're going to be fairly small probabilities, okay? But next, we have New York Avenue, B&O Railroad follows that, Pennsylvania Railroad, Reading Railroad, Tennessee Avenue, Kentucky Avenue, Waterworks, Free Parking, St. James Place, Atlantic Avenue, North Carolina, Indiana Avenue, St. Charles Place, Community Chest, Pacific Avenue, Vintner Avenue, Pennsylvania Avenue, Boardwalk, Marvin Gardens, Electric Company, States Avenue, Virginia Avenue, Short Line, Community Chest, Virginia Avenue, Income Tax, Connecticut Avenue, Oriental Avenue, Just Visiting Jail, Luxury Tax, Baltic Avenue, Park Place, Mediterranean Avenue, Community Chest, Chance, and go to jail. So if you feel like you just never, ever land on a chance, that's why. So I think that the next most interesting thing to look at is probably going to be looking at just the properties, right? Looking at which properties are the most likely to be landed upon. But before we do that, I do want to discuss these few columns that I hid over here, just so just for clarification's sake. So we do have a few differences that occur between my Markov process and the computer simulation. So we can see that Go and New York Avenue would be flipped in the simulation. Also down here, we can see that there are a couple of spots that would be flipped. So for instance, here, these two spots would be flipped between the Markov and the simulation. These two spots also would be flipped between the Markov and the simulation. And then finally, these two spaces down here, these two chance spaces would also be flipped between the two. So now that we know that and that we're good with that, let's go ahead and look at the probabilities associated with landing on just the properties in descending order. Okay, so looking here, the most likely property that you're going to land on is going to be Illinois Avenue, followed by New York Avenue, and then B&O Railroad. Those are your three most probable your three most probable properties, that you can land on any given turn. Those are then followed by Pennsylvania Railroad, Reading Railroad, Tennessee Avenue, and Kentucky Avenue. So what's really interesting here is we can see that the red properties and orange properties are fairly probable to actually be landed upon, along with a lot of the railroads as well. Now, sad part is the railroads aren't as profitable from a revenue standpoint, but that's okay. They are probable to be landed upon. Now down here, like what's the least likely properties that you're going to land on? So the least likely property you're going to land on any given turn is going to be Mediterranean Avenue, and that's actually tied with Park Place. So these probably may not be the best properties to get because not a lot of people are going to land on them. Followed in third by Baltic Avenue, third worst there. So what we see there is really the purples may not really be so great as a property choice in terms of just the probability of somebody landing on it.
Thanks for watching. Tune in again next time.